Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In today's lecture, we will discuss the quasi-static adiabatic process. Along with the quasi-static adiabatic process, we will also discuss the rigid experiment for measuring the value of gamma, and at the end, we will also discuss the Clark and Kidd's experiment for measuring the value of gamma. So this is a part of our lecture that has been taken from the course outline of thermodynamics, having the course code of PHY331. The learning objective from today's lesson is to understand the quasi-static process, and we also need to know the experimental experiment that is used for measuring the value of gamma, and at the end we will discuss the Clark and Kidd's experiment for measuring the value of gamma. So first we need to know what is the quasi-static process and how it could be performed. So for any quasi-static process, adiabatic process, in case of ideal case, the pressure, volume and temperature are changed according to the relation PV, V and TP and RP and T. I mean, so there is some relationship if we consider the PVT. So among the three variables are three coordinates, two of them are independent while the third one is a dependent coordinate. So based on this thing, even in the previous lecture we have modified the first equation line in terms of the heat capacity at constant pressure and constant volume. So we have written the equation like that: dq is equal to cv dt plus pdv. Further, when it was modified, it was equal to the dq is equal to cp dt minus v dp. So what happened if we consider an adiabatic feed process? So in that process no heat enters or leaves the system, so for that purpose dq will be equal to 0. So what happened, we can modify the above equation like that: cv dt plus pdv is equal to 0, or maybe you can move the vdp to the other side of the equation. It will be pdv is equal to cv minus cv dt. Similarly, in the second equation, if we put the dq value is equal to 0, so it will be like cp dt minus vdp is equal to 0. So as a result of that, cp dt will be equal to vdp. So this is something has been written over here in the next lines. So if we divide both sides by each other, so what happen, it will be like dp divided by p is equal to minus cp divided by cv into dv divided by v. So if we consider that Cp, the ratio between heat capacity at constant pressure and heat capacity and constant volume, is represented by gamma, that is a constant quantity. So the same equation could be modified like that: dp divided by p is equal to minus gamma dv divided by v. So this is something what we got, and we need to move forward for the integration or some from other purposes once we know the ratio between Cp and Cv. So dp divided by p is equal to minus gamma dv divided by v. So the equation can only be integrated once we know the value of gamma, and gamma is equal to gamma is actually the ratio between the heat capacity at constant pressure and heat capacity and constant volume. So for monoatomic case, the gamma is a constant quantity, but if we consider diatomic and polyatomic cases, then the value of gamma varies with temperature. So what happen, just like if we have a simple example for carbon monoxide, the temperature changes when its temperature changes from 300 to 3000 K. So the changes in gamma is decreased. I mean, the value of gamma is decreased from 1.40 to 1.29. So though this change in gamma value is a bit smaller, but anyhow the change is there. But when we perform adiabatic process, then there is no huge difference of temperature, because if you see in this example, there is huge difference of temperature, 300 to 3000 K. But for normal adiabatic process, there is no huge difference of temperature. So that is why the changes that are occurred in the value of gamma are often ignored. So for small temperature change, the value of gamma, the change in the value of gamma is ignored. So considering the gamma constant, the above equation could be written as, if we can integrate the above equation by considering the gamma constant, it will be out of the integral. So only what we need to integrate is dp divided by p into minus gamma is out of the integral is equal to dv divided by v. So what happen, it will be like natural log of p is equal to minus gamma natural log of v plus constant quantity. So what happen for natural log of constant, so if we move the p gamma to the other side, it will be like pv is equal to constant when we remove the natural log. So pv is equal to constant quantity. So this is something, the equation that hold for all ideal cases in the quasi-static adiabatic process. So consider the free expansion process, that is actually the adiabatic process but not a quasi-static process. When gas is moving towards vacuum in non-equilibrium state before achieving the final equilibrium state. When these compartments are the barrier in between the two compartments is suddenly removed, then the gas rushes toward the compartment that contain the vacuum, and in that case the equilibrium state of the system is not maintained. So in this case the system is in non-equilibrium state. Finally the system achieves the equilibrium state, but at that particular moment it is not in equilibrium state. So that is why we can consider this process to be an adiabatic, but it is not a quasi-static process. So the family of curves that is plotted on a PV diagram by assigning different values to PV, it could be written as, because here in this equation in the last slide you can see we can draw different curves by keeping by changing the value of PV is equal to PV P into v की power gamma is equal to constant. So we can assign different values to p and v, and this will be equal to a constant quantity. So all this could be drawn in this particular PVT diagram. So the slope of the adiabatic curve could be obtained like a change in p with respect to v at constant s, that is equal to minus gamma constant v की power minus gamma minus 1. So when we modify it, it will be like change in p with respect to v at s, that will be equal to minus gamma p divided by v. And the symbol s here what we have used describe the reversible adiabatic process. So we can now move toward the understanding of the rigid method for measuring the value of gamma. Gamma is something that is actually the ratio between the heat capacity of at constant pressure and heat capacity at constant volume. So we can use a simple experiment to measure that value. In this experiment there is a elementary mechanics concept are used instead of thermodynamics, and this experiment was basically developed by Reicher in 1929. So what are the contents of this experiment? The gas is enclosed in large jars having volume V, and a glass tube is fitted to the jar with an accurate bore of cross-sectional area A, into which a metal ball of mass M fits snugly like a position. So what happened? The gas is slightly compressed by the steel ball in equilibrium position, so its pressure is slightly larger than atmospheric pressure P0. So what happened? So if we neglect the mass fraction of gas, so what happen, we will have P is equal to P0 plus mg divided by A, and displacing the ball downward, it will oscillate with a period of tau, that is actually the time period. If the force is applied on the ball, it will move downward, and the pressure will move it upward, and by that means it will move up and down, just like oscillation will occur in the balls. And in this case we can consider the time period of this oscillation, that is equal to tau. So this is something. So how we can conclude from this thing? Here there are some superficial approximation what it has been considered the weight of the piston and the weight of the ball and the frictional forces are ignored. So due to friction, the ball is eventually come to rest, because this is a type of dissipative oscillations. So denoting the displacement of the ball from the mean position by y, the positive y means that the ball, when the ball is above the equilibrium position, and negative y means when the ball is below the equilibrium positions. So a small positive increase led to an increase in volume, which is denoted by dV. So we can write the change in dV, dV is equal to YdA, or this small positive displacement led to decrease in pressure, and that resulting force acting on the ball is equal to AdP, the change in pressure, that is actually the decrease in pressure. So dP is equal to F divided by A, and when y is positive, dP is negative, and would happen, the force also become negative, and the force is actually a restoring force trying to bring the ball back to its equilibrium position. So during the ball oscillation, the variation between P and V are considered adiabatic, and it is considered as a quasi-static adiabatic process. So you can apply the adiabatic condition for that, and for that PV ki power gamma is equal to a constant quantity. Further, this equation could be written for a particular case, that gamma PV gamma minus 1 dV plus VdP is equal to 0. So what happen if we can put this value of gamma over here? If we put the value of gamma over here, so we can have F is equal to minus gamma P A square divided by V into Y. So it is very clear from this equation that this is actually the restoring force, and this restoring force is directly proportional to the displacement, and it is in opposite direction. That is actually the Hooke's law, and this is the condition of simple harmonic motion whose time period is given by t is equal to 2 pi m divided by minus f divided by y under the root. So this oscillation is being compared are considered to be a simple harmonic oscillation whose time period is given as, and the force is actually the magnitude of that particular force which try to bring the body back to its equilibrium position. So if we apply the same values here for this particular case, so the tau will be equal to 2 pi mv divided by gamma p a square under the root. So from that we can get the value of gamma by taking under root on both sides. We are square on both sides. We will have gamma is equal to 4 pi square mv divided by a square p tau square. So from this we can get the value of gamma, that is actually the ratio between the heat capacity at constant pressure and heat capacity at constant volume. So the value of gamma could be obtained from this experiment, and it is equal to gamma is equal to 4 pi square mv divided by a square p tau square. So the value of gamma could be measured knowing the period of oscillation. The other factors are already known. So if we consider, or we can find out the value of gamma for this particular case, so the calculated value of gamma for carbon dioxide is in agreement with calorimetric calculated data. So the other experiment to measure the value of data is performed by Clark and Kids. But before understanding that particular experiment, we need to know some of the error that are in the some of the error are disadvantages in the Richard methods, and that disadvantages are the superficial approximation, as I already told you in the beginning of this experiment. The first thing is that it was considered that the case is ideal, but actually the case was not an ideal, that was a real case. The second thing is that the frictional forces were ignored. The frictional force due to the oscillation of the bars inside that particular region were ignored. So but actually in reality there are frictional forces exist. So what happened, the other approximation is that the volume changes are strongly adiabatic, but we have considered like that. So this is one of the drawbacks. So that is why the two other scientists, Clark and Kitts, taken into account these three disadvantages or maybe some type of drawback in the earlier experiment. They try to include these three factors to modify the experiment, and that was named as a Clark and Kitts experiment at Kitts and Kitts experiment in 1940. And the real equation of state, that is actually the frictional forces were considered, while the real situation is taken into account instead of adiabatic consideration. The second thing is that a steel piston at the center of cylindrical tube divides it by two parts, two compartment two. And similarly, the vibration of any desired frequency is set by external coils. So cylinder is kept at horizontal position at friction between the piston and cylinder, and the friction between the piston and cylinder is reduced by balancing the weight of the piston by an electromagnet. So this is the experimental setup of Clark and Kitts experiments. So here some advanced technology is used, and the already existing problem with the experiment has been taken into account. So with the microscopic equipped with micrometer eyepiece, the amplitude of vibration of the piston is measured. So its value is measured. Similarly, for the different values of the frequency are measured for the calculation, and finally the resonant frequency is calculated. So from the resonant frequency, after long calculation and precise calculation, the value of gamma is measured. So from all this calculation, finally the value of gamma is measured when the values are drawn over each other and the resonant frequency is clarified. So the value of gamma is measured finally. So the correction in the calculated values increased compared to the earlier experiment. If we compare the accuracy of the two experiments, in the case of Kitts experiment and in the case of this experiment here, the first experiment that was performed by this Archer experiment, in this case the calculation was a bit superficial, where here it has been considered that the weight of the ball has been ignored. Similarly, it has been considered that there is no friction between the bars and this walls of the jar. That was also then other approximation was that the gauge inside the vessel was considered to be ideal, but in reality is not ideal, it is a real case. So this is something what we got when we obtained the value of gamma from this calculation. So it was a bit different. I mean, it was not too much accurate, because and the problem or disadvantage with this experiment was the three disadvantage. So later on, these three drawbacks has been taken into account, and it has been modified in this experimental setup. Here you can see in this experimental setup, here is a gauge present over here, there is a piston in between the gauge, and there is a driving coils for it and the lift magnet to consider the weight of that particular, and similarly there are driving coils for that. So when it is taken into account and the values are measured for this, so there is a great accuracy of the system has been improved, and it is improved by 3%. I think the accuracy is improved by 3% in the previous experiment, but actually in the both experiment it was considered it was the objective of both experiment to find the value of gamma, that is actually the ratio between the specific heat at heat capacity at constant pressure and heat capacity at constant volume. So in both cases this heat capacity is calculated, but the accuracy of the last experiment is a bit higher than the accuracy of this Richard experiment, and the reason for this improved accuracy are the three. And these three reasons are: the first one is that the case is not considered ideal, and the other is that frictional forces are taken into account, and the volume changes are considered as a real volume changes instead of the ideal changes. So this is something about the Clark and Kate's experiment that has been performed to find out the value of gamma, that is actually the ratio between heat capacity at constant pressure and constant volume. So this is some discussion about today lectures. We can move to our next lecture in the upcoming classes. Thank you very much.